3 billion emails. It's not just, the volume is not just that large, it's also very diverse too. So we have user attributes, page attributes, segments, there's SMS and push notifications, Twitch and Facebook updates, and many, many more. So in order to handle this kind of data, obviously we'll need distributed computing. So our Spark journey starts in about 2014. So when I joined this startup called Krux at the time, and later on it became Salesforce Marketing Cloud Audience Studio. So at that time, Spark Krux is already dealing with a lot of data. It's seeing a big chunk of the internet, mainly because it's the data platform that handles big clients like New York Times, BBC, Warner Brothers, and Nielsen at the time. So it's pretty big. So we need distributed computing at that time already. So in that time, we were using Hadoop. So to use that, at that time we have these services mainly to just powering match queries, schematizing ETL jobs that ship data from one places to the other with some very basic and simple analytics capabilities. So it was okay. It was manageable. We spin up a lot of EMR clusters and tear them down every day, but it was okay. However, when we start to introduce more advanced analytics and features that's backed by machine learning and data mining things, Hadoop becomes the bottleneck, basically. The reason being, first of all, the code base is really verbose. You have to write a lot of code to achieve very simple application logic. When you start to writing also slightly more complex applications, you actually need to chain all these MapReduce jobs and be able to manage the intermediate data in between too. So, and because of this, all your application logic gets split across all different parts of the source code. It's very hard to read and reason to. At last, it's painfully slow because of you need to serialize and save all this data in physical storage between each MapReduce cycle. So that's just a lot of wasted computation there. So at that time, I already had pretty good experience working with Spark in my previous job building a relatively large-scale analytics system, and that was just Spark, I think 0.9 days. But at that time, I already loved it. This problem I had to deal with, but it just offers so much more potential there. So, it seems like a no-brainer to just at least implement those more advanced analytic capabilities in Spark. So we did it. So here's some examples when you just try to calculate these simple things in Hadoop. And this is what you do in Spark. So obviously it's much less number of code, it's more concise, but that's not just the whole point. These are the typical code you would typically write when you're working with any collection libraries or just the standard collection libraries in Scala. So all of those distributed concept and the machinery get abstracted away, and you can understand what the code is trying to do just by looking at those a couple of lines. So that's great. And because of this, the developers can concentrate more on the actual model algorithm, whereas you spend much less time worrying about the intermediate storage and memory management. And we see a massive reduction of the failure rate in one of the jobs. And this is a comparison of one of the machine learning pipelines that we had before with pretty highly optimized Hadoop code. So for small number of clients, so for small size clients, you see about 30% improvements. But for larger clients where the I/O cost becomes more dominant, you see more improvements, about 65%. As a result, because of less number of failure rates and faster running time, we have a much lower cost. All right. So what you see is concise, readable, and performant code. We also find out, like for very simple workflows, Spark is slightly less reliable. But overall, given all these other benefits you're getting, you actually result in a much more stable system overall. Okay, so typically the situation is when you're trying to solve certain problems, you introduce a new solution. What you typically get is that new solution will solve a whole bunch of your existing problems, but it will give you a set of new problems. But in this case, hopefully better ones and the ones you want to work with. The first one that we get is technically not about Spark, but it's about Amazon S3 and how it interacts with HDFS. We here at Salesforce, we use Amazon AWS S3 to manage and store our data. So there are two main things that's not really desirable here. Is first of all, S3 is an eventual consistency system. So that means when you if you update the data, it's not always available. If your workflow is always appending data to your data to S3, that's fine, because S3 has this read after write consistency model. So you're most likely fine there. However, if you want to start update, delete, and overwrite, you will suffer the case in terms of dirty read or some other undesired behavior. So you need to think about these situations at the start of your workflow in order to deal with them. The second one of them is although S3 is compatible with HDFS on the API level, it's not really a file system. Right? You might construct your, it's actually a key value store. You might be able to construct your keys to make it look like a file system, operating like one, but in reality, it's not. This will cause certain problems, like if you have a lot of folders to work with. Say, you have a job that will union data from 1,000 folders, for example. How Spark does it is first, we'll go in there, list all the files in those 1,000 folders, trying to find the files, and then plan for the next step execution. What it does is in the master node, it will issue 1,000 of API calls to S3 and find out the content. These are network calls, and typically takes about 1 to 2 seconds to finish, and it's done in a serial fashion. So that means you're spending 30 minutes just to find which files you want to process before you're actually processing them. And this is done on the master node, meaning all these 30 minutes, the executors are staying there doing nothing, and you can't scale them horizontally. But however, what typically happen is these 1,000 or many folders typically have the same parent folder. That means if you know the folder structurally beforehand, you can actually just call the S3 APIs directly, find the files yourself with 1 or 2 or 3 API calls, and then construct an RDD of those file paths, and then call flat map. You can actually get the files yourself and read them there. This way, you also achieve distributed reading and processing as well. So typically, a 30 minutes operation becomes about 10 seconds, for example. All right, next, joins. So join is not just Spark, it's a very common operation in database. It's also one of the hardest problems in database researches. So in Spark, when you're dealing with RDDs, all the standard query optimizations apply too. That means you do selections, filter, aggregation as much as possible before the join. that will give you a lot of performance gains. There's also, in certain cases, you might have skewed keys, meaning a lot of entries belongs to a small portion of the keys. In that case, when you're trying to do the join, it will have all these large number of entries into one executor because they share the same key, and then you will have memory issues if they don't fit. One trick is you can introduce certain noise in those keys, so that will break them down, and then doing some multi-staged join. Another way is you can split data into data with sparse keys and data with dense keys. And in the sparse set, you can just do a normal join because you have more uniform distribution. On the dense side, you can do a broadcast join, and then at the end, you need the results. So speaking of broadcast joins, it's a common technique that you need to that people employ when they deal with imbalanced joins. What imbalanced joins means you have two data sets. One is they have very different sizes. One is probably very small, and one is probably very large. For the smaller one, if they do fit into the memory, you can actually just broadcast that join, that smaller data set into all the executors where they will have all the information available, and then all you do is a matching. So that will save the cost of shuffling and co-grouping, so it will improve the performance a lot. If the smaller data set is not smaller enough to fit into the memory, you can also do the similar trick by just build a blue filter of the keys in the smaller data set, send that over, and then filter the larger data set. In that case, the larger becomes smaller, and the join is more balanced. That will typically work pretty well too. All right. Next one is persistence. When I heard about Spark, one of the most exciting features that I think is persistence. What it does is you can ask Spark to save the intermediate results in memory or disk, so that you don't have to recompute it if it gets reused a lot, for example. However, in practice, we found this never really worked. So the main thing is probably with Java serialization. So when at least in RDD APIs, when it does persist, it will do the Java serialization, which is costly, consumes a lot of memory, and that cost actually compared to recompute is higher. So that is one, and the other one is the intermediate data sets where you typically want to persist are typically large. So in that case, that intermediate data set will consume a lot of memory or disk. That means less is available for the subsequent operations, and there's a lot of management overhead too. What we found is actually not calling that. The RDD API actually does a pretty good job of just avoiding recomputation itself pretty well. So this is what we did. And I think it probably works much well in the newer data frame and dataset API because Java serialization is probably not used. Speaking of data frame and datasets, there's something that is undesirable too. So first of all, it works pretty well if all you do is running one single query, and the result is what you need. So I think that the Catalyst Optimizer API does a really, really good job in terms of optimizing the query and trying to do the right thing. But a lot of the cases that what we did is we actually need to implement discrete algorithms using plain Scala code. And type safety really helps a lot there. The dataset part of the data or Spark SQL API does offer some of the type safety, but when you start to get more complex operations like joins, it's pretty awkward to write them in a type safety way. So that's one thing. The other thing is if you have multiple queries in a workflow, and you have one query and you have 2, 3 other queries, depending on the result of the first one, and what we typically find out is that the first query gets executed again and again and again, and we have to call persist to ask Spark to not recompute it. So the previous benefits we get from the RDD API does not seem to be there anymore. But those persists, although it's better, it's still not free. And a lot of cases we found out when we change back to the RDD APIs, it actually gets a lot of performance gain too. Having said that, the ML pipeline-based implementation that we found in Spark MLlib actually works pretty well. So I think it's because when we're adding those stages to the pipeline, and the whole thing becomes one big execution operation, and then you will have the global knowledge to be able to optimize that. So we start to exploring more and more by using, for our new algorithms, to use the ML pipeline-based approach. Okay, so in order to support the features, what typically happens is you can't support that with one single job. You need a set of Spark jobs to be able to support what we're trying to deliver. Some can run in parallel, some need to have other dependencies. So this is how we trying to orchestrate them. We have this framework. First of all, there's a way to generate to write dynamic pipeline recipes, and that will be given certain situation, generate pipeline instances that gets deployed to the services, and the service will be able to spin up resources, deploy activities to those resources, and manage the dependencies there. To give you some idea of what we are running to support all our applications, we have about 900 of those recipes every week. That in turn deploys about 8,000 pipelines, and every week we have about 30,000 EML clusters to support all these things. Some applications that this supports is the 6 billion daily predictions for Einstein engagement scoring, and 20 trillion weekly predictions for our lookalike predictions. So to operate things at this scale, first of all, it costs a lot. And second, we're actually constantly seeing the limits of the cloud. So where the failure becomes norm, every day we're seeing network issues, unhealthy nodes, throttling limits, and out of capacity from AWS. So in order to do that, we need to consider cost optimizations, of course. And on the framework level, we will need to be able to handle automatic retries. We need to set timeouts to all resources and activities. We need to have the activity and resources supervised by external services. And when all these things fails, we need to support painless bad views. To have that, there's a resource optimization service that's constantly being aware of AWS capacity, availability of different node types, what's the spot market doing, so that it can bid on instances that's cheaper. And the recipe manager will get those information and construct the pipelines with the right configuration of the resources. And once that's implemented, once that's constructed, we'll submit all these configurations to the pipeline service, where it will manage services and deploy tasks to those services. So this is a bit different from a traditional workflow management system like Airflow, where the resource management responsibility is passed to the task, and that will have the effect of where if the task is crashed in the middle, that have the risk of having rogue unmanaged systems. So we found out, so for our case, we actually need such external services that is also managing the resources as well. So the recipe manager, our implementation is called Starport. The pipeline recipe can be constructed by a library called Hyperion, and the resource optimization service is called Diviner. So Starport on Hyperion is now open source under the Crux GitHub repo, and we plan to open source Diviner soon. And we also leave the rest to AWS services like AWS Data Pipeline and the rest. So to illustrate how you would utilize Hyperion to construct a pipeline, so if you have your Spark job published in S3 directory somewhere, all you need to do is specify where it is, and you want to run it in an ELN cluster and with Spark installed. To add alerting is very simple too. Just need to add on fail or on success depending on your situation. You can set different number of retries, and there's a DSL to help you specify the dependencies. That means if you run, in this case it means you start with task 1, and then only when task 1 finishes, you can start both task 2 and task 3, and only when both task 2 and task 3 finishes successfully, you start task 4. And there's apply that built in for you to run simple backfills. All you need to do is specify the date, when the pipeline is supposed to start, so it will run as if it was run yesterday in this case. In the end, I hope you find something useful today. I want to share this quote from one of my favorite authors, Yuval Harari. If you want to create a better world, the key is to set data free. Thank you.
Thank you, guys. We'll take a few questions if you guys have any questions. I need to do my 10,000 steps, so I don't know the mic. You have a question?
Yeah. Does he have a paper coming out on this at all, or is it something that's going to be published that was really interesting? There's a lot of steps involved in there that sound fascinating.
We don't have one planned, but if you're interested, we can definitely, or we can go into more details too in future meetups, I guess, or other.
You have a question?
You mentioned AWS S3 has a problem when the data is very long. Have you considered other kinds of cloud?
We are. There are other clouds, but current operation is mainly based on AWS. That's why we're using S3. But even in other places, I think the eventual consistency does not seem to go away. So that's something we need to embrace, I think. Delta Lake will solve a lot of those problems.
You mentioned having problems with Airflow. Could you go into more detail about what problems you had with that? Airflow?
You mentioned you had some problems with Airflow. Can you elaborate?
We don't have a lot of problem with it. It's mainly when we designed it, we think we don't want the task itself to manage resources. We want the service to be. And because there's so many of them, like you see the number of VMware clusters, we constantly spin up and down. So if we leave that to the task to manage that, it's very likely to have rogue instances or clusters going there unmanaged. We have to have some other things, maybe monitoring that. And also, the data pipeline service itself offers that solution too. So So that's where we're going with.
We'll take one more last question.
Yeah, I don't think that is wrong. So how big is the tables that you are hitting on an S3, and whether you typically retrieve the whole 5 tables from an S3 bucket that you're hitting?
So the table itself, it depends. There are raw logs that just like HTTP request or log in a JSON format. So there's a whole lot of subsequent jobs to take that, organize them into tables. It could be Hive tables. Some we use Avro, some we use Parquet, some we use in plain text. Depends on the situation. So there's a lot of things in between.
Do you experience the performance decrease when you're retrieving the data from S3?
The performance is okay. The optimization mainly is on the size of the file and how many files you have given a prefix. So if you have a lot of them in a prefix, like if you have 20,000 files, it's not going to work very well because of the listing cost. And if you have very large file, if you're choosing the wrong compression, like if you have 5 gig file with gzip, that won't work very well either.
Okay.
What's
Thank
the
you.
one you made open source?
There's 2 libraries. One is called Hyperion. That's the library that you can use to construct those pipelines and interact with AWS data pipeline. The other one is called Starport, which is managing Hyperion pipelines.
Give a big hand to Sharon. By the way, we are going to publish the slides, so you'll actually have all the material, so you don't have to frantically write that. So thanks a lot, Sharon. Now.